Ever stop and think about how a simple piece of metal, just a wire, can literally pull a signal right out of the air and connect us to someone on the other side of the planet? It's kind of the unsung magic of the antenna, right? It's the fundamental piece of our entire wireless world. Today, we're going to pull back the curtain and see how this simple device actually works, from its accidental discovery all the way to the complex systems packed inside your phone.
All right, so let's kick this off with a story of, well, accidental genius. It all starts over 100 years ago, when the new frontier of radio waves was just being explored. And as it turns out, all the good territory, it seemed, was already taken. So back in the early 1920s, the big players, we're talking commercial and military operations, they dominated the valuable long-wave radio frequencies. Amateur radio operators, the hams, they were basically kicked off the good stuff and pushed onto what everyone thought were useless frequencies below 200 meters, the short waves. The thinking was, those signals are worthless, they go nowhere. But then something amazing happened. These amateurs, broadcasting from their backyards, started talking to each other across continents. They had accidentally discovered the incredible power of what everyone else had literally thrown away.
And that discovery brings us right to the big question we're going to answer today. What is going on here? How can a simple piece of wire tap into these invisible forces and tie our whole world together? To get that, we have to get back to basics.
See, to understand an antenna, you first have to understand what it's interacting with. It's not just a passive chunk of metal. It is an active transducer. That's the key word. It's a device specifically designed to convert electricity into an invisible, traveling force, the electromagnetic wave, and then, just as important, to turn it back into electricity.
So what is this wave exactly? It's called a transverse electromagnetic wave, or a TEM wave. I want you to picture two waves, and they're dancing together in perfect sync. You've got an electric field, let's say it's oscillating up and down. At the same time, you have a magnetic field oscillating left and right. They are always at a right angle to each other, and they're also at a right angle to the direction they're traveling in, just hurtling through space together at the speed of light. An antenna, well, is just a perfectly shaped net built to catch that dance.
And the whole relationship is governed by this beautifully simple bit of math. The frequency, f, multiplied by the wavelength, lambda, always equals the speed of light, c. Now that's more profound than it sounds. It means if you know a signal's frequency, say your favorite FM station, you automatically know its physical size, its wavelength, as it zips through the air. And that physical size, that is the secret to building the right antenna to catch.
Okay, this brings us to two absolutely critical ideas, resonance and impedance. Think of resonance like striking a tuning fork. An antenna is resonant when its physical length is perfectly sized for a signal's wavelength. When that happens, it vibrates electrically with incredible efficiency. But that's only half the story. At the exact spot where you connect your radio to the antenna, the feed point, there's something called impedance, which is basically the opposition to the flow of electricity. For the perfect handshake between your radio and that antenna, the impedances have to match perfectly. You got to get both right for the magic to work.
So let's take all that theory and actually build something with it. We're going to start with the most fundamental antenna of all. You can think of it as the blueprint, the Adam and Eve of antennas, the half-wave dipole. And just like the name says, it's a piece of wire cut to be exactly 1/2 of the target signal's wavelength. So, what happens when you pump energy into this wire? Well, imagine you're holding a rope that's tied to a pole. If you whip it, a wave travels down the rope, hits the pole, and reflects right back at you. The wave going out and the wave coming back interfere with each other, and they create this stable pattern of peaks and valleys that just looks like it's standing still. The exact same thing happens on a dipole. The transmitter sends a wave of energy down the wire, it reflects off the ends, and the two waves combine to create a stable oscillating pattern of voltage and current. We call that a standing wave.
And right in the dead center of that standing wave, we find the sweet spot. At this point, the current is at its absolute maximum and the voltage is at its minimum. This very specific condition creates a feed point impedance, in a perfect world, of 73 ohms. That number, 73 ohms, that's the holy grail. It's the target that our radios and our cables are all engineered to match up with.
And this shows us exactly why that center point is so important. See, the impedance isn't the same all along the wire. It's nice and low at the center, but as you move out toward the ends of the wire, where the voltage is peaking and the current drops to basically zero, the impedance just skyrockets into the thousands of ohms. So you can't just hook up your cable anywhere you want. It has to be at that very specific low impedance point. So what does the signal actually look like coming off this thing? Well, it's not a perfect bubble of energy going out in all directions. The dipole pushes most of its power out broadside to the wire, creating these two big lobes of signal. It looks like a classic figure 8. But right off the ends of the wire, there are these deep nulls or dead zones where there's almost no signal at all. This is the antenna's directivity.
Okay, so we've got the basic dipole down. Now for the fun part. This is where engineers spent the next century getting really clever, modifying this simple design to solve all kinds of problems, like how to focus the signal or, how to make the antenna a lot smaller.
So, problem number 1 is direction. That figure 8 pattern is fine if you're a radio station trying to cover a whole city. But what if you need to shoot your signal to one specific spot, maybe hundreds of miles away? The solution is the brilliant Yagi-Uda antenna. You've definitely seen these on rooftops for getting TV signals. It takes our simple dipole and evolves it into a highly focused signal beam.
So how on earth does it work? Well, you start with your regular dipole. That's called the driven element because it's hooked up to the radio. Then you put a slightly longer metal rod, a reflector, just behind it. It acts like a mirror, basically bouncing any signal that's going backward and pushing it forward. Then, in front of the dipole, you place one or more shorter rods called directors. These act like a lens, grabbing all that energy and focusing it into a tight, powerful beam. The more directors you add, the tighter and stronger that beam gets.
All right, next problem, physical space. A half-wave dipole for the AM radio band could be over 250 feet long. Not exactly something you can stick on your car, right? The solution here is a really clever electrical trick called a loading coil. A short antenna is just naturally, well, it's not the right length. So by adding an inductor, which is just a coil of wire, we can electrically trick that short antenna into thinking it's the full proper resonant length. It's a bit of electronic magic.
And this table really shows the trade-off. If you want to shrink an antenna to about 80% of its natural size, you need a coil that gives you about 160 ohms of reactance. But look what happens when you try to shrink it all the way down to just 40% of its full size. You need a whopping 1,800 ohms of reactance. The takeaway? There's no free lunch. The smaller you make an antenna physically, the harder you have to work electrically to make it resonate.
Okay, we've gone through the core theory. Now let's bring it all home. Let's look around and see how these exact same principles are at work, usually hidden in plain sight, in the tech that you use every single day.
And I mean it. They are everywhere. The phone in your pockets, that Wi-Fi router in your living room, the GPS in your car, those huge satellite dishes, even the little RFID security tags in stores. Every single one depends on these fundamental rules of resonance, impedance, and directivity.
Let's just take your smartphone. Inside that case isn't just one simple wire. It is a crazy complex system of little metal traces etched right onto a circuit board. But if you actually look at how it's designed and modeled, you can see it's a direct descendant of that simple dipole we talked about. It's just an intricate, miniaturized grid of wires, all precisely engineered to resonate on dozens of different frequencies for your cell signal, Wi-Fi, Bluetooth, and GPS, all at the same time.
Or look at a giant satellite dish. It might seem like it's from another planet compared to a rooftop Yagi, but the physics is identical. Instead of using a simple metal rod as a reflector, it uses that massive parabolic dish to collect incredibly faint signals from space and focus them all onto one tiny point, the feed horn. It's all about gain and directivity, just on a cosmic scale.
And finally, let's go back to that humble whip antenna on a car. For the FM band, it's a pretty simple vertical antenna. But for those much lower AM frequencies, that whip is way, way too short. So what do you think is inside that little black plastic base? Yep, often it's a loading coil, doing the exact same job we just talked about, electrically stretching that short whip so it can resonate on those much longer wavelengths.
So there you have it. From a simple wire in a backyard bouncing signals off the sky, to the elegant physics of impedance, to the miniaturized marvels we carry around in our pockets, we've seen how one simple principle can literally connect the entire globe. We've pretty much mastered the simple wire. But now, as our world gets more and more saturated with this invisible data, the real question is, what's the next frontier? What's the next chapter in the story of the antenna?